Good morning, doctor. I am Linkesss, student 1. Now I will explain the linear static analysis for the aircraft engine bracket. This analysis helps to verify whether the design can handle the applied load without excessive stress or deformation. The criteria we targeted were a mass below 0.8 kg, a factor of safety between 1.2 to 3.0, and maximum deflection below 0.35 mm, that is millimeter. The present design achieved all targets successfully. The bracket is mass is 0.74 kg, which is within the limit. The factor of safety is 2.7, showing the design is safe under load. Deflection is only 0.18 mm, which means the structure is quick rigid. We also calculate the percentage difference from the benchmark. The mass is 7.5% lower, the factor of safety is improved by 125%, and the deflection is reduced by 48.6%. This shows the new design is lighter, safer, and more resistant to bending. Compared to the original bracket, the new design is 64.9% lighter, the safety factor is 157% higher, and the deflection is reduced by 58%. This improvement means better performance, longer life, and improved reliability. Among the three designs, we choose design 3 because it offers the highest factor of safety of 2.7 compared to 2.5 in design 2 and 2.2 in design 1. A higher factor of safety indicate that the bracket can withstand more stress before reaching failure, which is critical in aerospace application. The bracket is made from aluminum alloy 7050 T7651, which is known for its high strength and excellent fatigue resistance. By choosing the design with the best safety performance, we are maximizing the benefit of the material properties. In addition, design 3 also showed the least deflection, which means it is more rugged and will maintain its shapes under load. This improves the reliability of the component in real life use. Therefore, from both a safety and performance standpoint, design 3 is clearly the best option. The on-visor stress distribution shows the maximum stress is 184 MPa, which is well below the yield strength of the material 490 MPa. The red areas indicate higher stress, especially around the holes, but overall most parts of the bracket are in the safe zone. From the deformation results, the maximum value is only 0.18 millimeter at the top cylindrical area, which is acceptable. The base has almost zero deformation due to the fixed support, so the bracket holds its shape well under load. The factor of safety shows that most areas have high safety margins. The lowest safety factor is 2.7, still much better than the original design factor of safety of 1.05. This confirms the new design is safe and reliable. This is result for equivalent stress, result for total deformation, and result for safety factor. That's all from me.
Okay. Good morning, Dr. Ikman and Dr. Mas Nizam. I am RISHIKESHAN, son of THANABALAN. Today I am going to present about design improvement and analysis of aircraft engine bracket. We are from group 11. We are total 3% and I am Rishi. Uh, in this presentation, I am the student 2 who presents about thermal analysis. So for the first part, I would like to present about the key factors contributing to thermal effect. First factor is thermal expansion of material. The bracket is made of aluminum, which expands when exposed to heat. In the simulation, the temperature was increased from 25 degrees Celsius to 150 degrees Celsius. Since the bracket is constrained at mounting holes, the expansion is not free, resulting in built-up internal stresses, especially around the hole regions. Structural constraint effect is the second factor. Fixed support at base and constraint around bore holes resist expansion. This causes the bracket to experience stress concentration in localized regions, leading to higher von Mises stress and deformation, even though the material stiffness modulus was kept constant in the simulation. For the next part, there is a table contains parameters without thermal effect, with thermal effect. So the parameters, and these are the result on the right side. For maximum stress is without thermal effect is 183.98 megapascal. With thermal effect is 1146 megapascal. Heat causes major stress increase due to restricted expansion zones like bolt holes. For the next part is deformation jumps from 0.18 millimeters to 0.50 millimeters with thermal effect. And factor of safety drops from 2.7, which is safe, to 0.43, which is high risk. The stress concentration is higher stress built near the bore holes and top cylindrical features with thermal effect, which is compromised under heat. But for without thermal effect, it is strong and stable, and within the spec that is asked in the lab guideline, project guideline. The simulation notes is no temperature dependent properties used, only thermal load was added. Material behavior is stable for without thermal effect, and with thermal effect, the material expands too much when heat is applied and modulus not varied. And for conclusion is design work well under static load, but it is not safe for higher temperature conditions. For next part is the result of thermal stress. We can see the equivalent one meter stress, which is 1146 megapascal, and next is the total deformation is 0.50 millimeters, and the thermal factor of safety, which is 0.43. And for last part in thermal stress analysis is material selection. Aluminum alloy was chosen for its high strength to weight ratio because aluminum is one of the lightest material we can find, and it has good corrosion resistance and ease of machining. However, its high thermal expansion caused significant internal stress under constrained conditions. The factor of safety dropped from 2.7 to 0.43 due to solely thermal expansion, showing that while strong under load and material lacks thermal stability without design adaptation. The future considerations is design improvement could include adding thermal relief features like cutouts near bore holes, adjusting constraint to allow limited expansion, and reinforcing high stress areas such as top cylindrical section. Alternatively, switching to materials such as magnesium alloy or INVAR, which is low thermal expansion, stainless steel 316L for better thermal resistance, or titanium alloy could be used to improve performance under temperature changes. However, we have to do further simulation and testing to make sure the materials are under the spec given in the project guideline. So that's all from me, Doctor. Thank you. For the next part, will be presented by IRFAN for free vibration analysis.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan bin Abdul Karib. My matric number is 231313640. Okay, saya akan continue. My part is free vibration. First, what is free vibration? Free vibration is in computer engineering. We use computer programs like ANSYS and or SolidWorks to know how real parts such as car body, airplane wings, and machine parts vibrate after being distributed selepas dikenakan force. Okay, apa yang kita nak tahu kat dalam free vibration ni, apa yang terjadi kepada part kita tu adalah how fast it vibrate, what shape it vibrate, and the last one is the vibration after being distributed. Okay, dalam projek ni telah ditetapkan natural frequency yang telah ditetapkan oleh lecturer adalah 275.8 Hz, dan kami memilih untuk menggunakan design yang ketiga kami yang didesain oleh LINKESS, dan design ini dapat menghasilkan natural frekuensinya adalah 6334.9 Hz, dan maximum deformation yang telah terhasil juga ialah 86.248 nm. Bahagian merah yang terhasil dalam kawasan bahagian merah yang terhasil dalam design yang ketiga ini adalah di bahagian bawah, hujung bawah surface part, and then the blue area hanyalah di bahagian fixed support, keempat fixed support, dan the yellow and green, also the orange is the transit between stable and high stress zone lah. Okay, kami menggunakan design yang ketiga ini kerana design ketiga ini menghasilkan natural frequency yang paling tinggi dan lebih selamat lah, lebih sesuai. Okay, kita akan teruskan ke design yang pertama yang dihasilkan oleh Rishi. Design yang pertama ini menghasilkan natural frekuensinya adalah 3424.5 Hz dan maximum deformationnya adalah 98.692 mm. Okay, red zone dia, kawasan merah dia terhasil di bahagian pemegang part lah, and then the blue zone is also at the fixed support, and then the yellow zone, green zone, and then the orange zone located around the central body. Okay, design yang kedua yang dihasilkan oleh saya adalah dapat menghasilkan natural frekuensinya ialah 4545.6 Hz dan maximum deformation yang terhasil daripada design ini adalah 68.814 mm. Okay, red region dia, red zone dia adalah di kawasan belakang part, dan the blue region at the fixed support, and then also the yellow, green, also and the orange at the represent moderate deformation levels lah, and then show the transitional area between stable and higher stress zone. Okay, antara yang ketiga design ini kami menggunakan design ketiga kerana ia menghasilkan natural frequency yang tinggi, so dia dapat serap natural frequency yang telah ditetapkan oleh doktor. So ya, itu sahaja daripada saya. Terima kasih.